Hello dears. This week we are going to study or we are going to discuss the theory of analog to digital converter. Analog to digital converter is an electronic circuit which having an analog input and the output will be digital. The analog input is, as you see here, a signal which having a variation as a function of time. But when it comes to the other side, here we are having a sampled signal, not yet digital. You will see this after a while. It's given as magnitudes. In analog to digital converter, we are going to start with the sampling. Then after that, we are going to go to the digital. Most of the transducers we are having producing this kind of signal. Most of the transducer or most of the sensor introducing or generating this kind of signal. On the output of the analog to digital converter, we are going to put the signal in a form which is suitable for computer. That's what we are going to discuss after a while. Analog signal is directly measurable quantities in terms of some quantities. Means, for example, if I want to measure the light as a function of time, maybe I can say the light, we are playing with the light, and here we are having light sensor. So if I am increasing the light or decreasing the light or keep the light steady state or whatever, we will find that the quantity of light measured with respect to time. When I say measured here, because the data of measurement, the parameter I want to know about the light is stored in the magnitude of the light. So I can say the light is increasing to the maximum, light is decreasing. These are the value of light stored in the signal. We can see in the shape of the signal. Let us look at these characteristics. Hopefully it will make us clear about the analog signal. It's having maximum and minimum voltage. As I mentioned just now, the data means the light by itself is stored in the magnitude of the voltage. Precise continuous signal. So it's a continuous signal. Continuous. It's not going to stop at any time. If it's stopping, means the input signal is not there. That's what it means to us. Rate of voltage change. There is a rate for the change in the voltage. So we are concerning about how the voltage is changing as a function of time in terms of, or as a function of other parameter. How this magnitude is changing in terms of this variable. Frequency is not a steady state signal. I can say frequency if not a steady state signal. I mean, there is a frequency for this signal. We cannot say there is 100% frequency because it depends on how the signal look like. If the signal is a steady state, the output will be steady state. Means if the light here is same quantity, the light is not changing, the output going to look like straight one. If we are changing the light, coming from the input, you are going to find the signal measured is going to look like it's changing as a function of time. So the frequency of the output is proportional to the frequency of the input signal. Here is analog signal. There is analog signal. If you notice, we are having time here, and here is the magnitude. At any instant of time, there is value. At any instant of time, there is value, and the value is stored. Telling me about the data measured. Again, I am repeating. Here I can say, if I ask the magnitude, let's say this is measurement of temperature. So what is the temperature here as compared to this one? You will find that here is smaller. Temperature is increasing, then temperature decreasing. Then it could go back to increase, then decrease, and so on. So here, what's happening in the temperature can be seen direct in the signal, in the analog signal. Example on that is the thermometer or the car speedometer. So as I mentioned just now, any change in the input will be met by change in the electrical signal on the output. That's why we call it analog signal. How about digital signal? Digital signal is not a continuous signal actually. The digital signal is not a continuous signal. It's just a form of ones and zeros arranged in certain way. So if I say this is, for example, temperature, what is the meaning of this one is in terms of temperature? Here it's not clear. The signal is not telling us about the temperature. The arrangement of ones and zeros can tell somehow to some circuits how the temperature is increasing and decreasing. So I just want to say here, signal is not, we cannot read the signal direct from here. We have to read it by other devices. But the signal of digital is going to be 0 at some times, then 1, then 0, then 1. And there is no other data, either 1 or 0. And that's it. So you will tell me where is the data, where is the temperature, for example. As I said, it's in the arrangement of ones and zeros. Like here, 1, 0, 1, 0, 0, 1, 0, 1, 1. Maybe it's going to be followed by 1, 1, 1, 0, 0, 0, 1. So it's different data. Maybe it's going to be followed by 1, 0, 0, 0, 0, 1. So that the data or the change in data is going to be seen by the arrangement of ones and zeros. He's giving here example on light switch can be either on or off. That means sometimes if I want to check, for example, if you open the refrigerator, if you get this point, if you open the refrigerator, the light will be on. The light inside will be on. That's on or off. That's one thing. Maybe the example is not strong enough. Let us look at other example. When you go to the door, automatic door, once you are close, approaching the door, so the door will open. So here I don't care about the quantity of the migrant, the quantity of the man who is entering. That's not, I don't need it that much. All what I need to know is there a man? If yes, door will open. If no, door will not open. So the signal will be either on or off. On or off. And always it depends on the application, as I mentioned. Sometimes it's in this application like this. In other application, the arrangement of 1 and 0 is going to tell us about the data. In the analog to digital converter, it's the circuit which going to take on its input analog signal, and the output analog to digital means this analog signal will be converted to digital. The analog will be converted to digital. So analog to digital converter, it's the circuit which taking analog signal, and on the output it's producing digital. Notice that digital signal is not going to be positive and negative. It's not like this. Digital signal, it's going to depend on a number of bits. So maybe we have 4 bits signal, or maybe 8-bit signal, or any other 1, 2, 3, 4, 5, 6, 7, 8, or 8-bit signal, maybe 16-bit, and so on, or any other, maybe 5-bit. So when I want to consider the conversion, I need to know what will be the output on the analog to digital converter. So there is the signal, which the analog signal is going to be produced in a term of bits. Means if the input here is 5 volt, the output may be in a 3-bit. Maybe it's going to be 110. If it's 8-bit, maybe it's going to be something else. Okay, that's what we mean by number of bit. Maybe 4-bit will give us different value. It's something like this. So all what I need you to know here at this stage, that this 5 is going to be converted to ones and zeros proportional to that 5. Remember here, I don't mean converting decimal to binary. I don't mean this. But you can keep the idea of decimal to binary in your mind while thinking about this point. Okay, analog to digital signal. The analog to digital signal is used to process or store the data. I want the analog to digital converter so that I can store the analog signal or display it sometimes to process it. Just to give you a small example, if I want to measure the voltage, of any resistor or any quantity of voltage we want to measure, we can measure it by this kind of voltmeter. Where we are having pointer, and the pointer will point at the voltage we have. This kind of voltmeter is analog. We call this one analog meter. So this kind of meter is analog. But if I want to have the one which very famous, you have seen in the lab maybe, if I want to have this kind of voltmeter where the display is going to be as a number, the display will be as a number. If I have this kind of meter, this is called digital meter. This kind of meter called digital meter. So to display the data digitally, we have to have analog to digital converter, inside the meter so that we can display it in a digital way. I hope you catch the point now. That's one of the elements where we can keep the analog to digital converter in. But keep in your mind, this is not only to measure the voltage, also we can measure the thermometer, the temperature. We can measure the temperature. Sometimes in the oscilloscope, we need analog to digital converter. In the cell phone, your hand phone, also there is analog to digital converter. Keep in your mind that when you want to save your sound, your voice is analog. If you want to save it inside your computer or inside your handphone, it has to be in digital form. That's why we convert it from analog to digital. For that, we need analog to digital converter. The microcontroller or microprocessor, it's the device which doing the processing in the computer. So inside the computer, there is something called brain. Sometimes we call it the brain of the computer, which is the microcontroller. I think everybody is familiar with this term. So the microprocessor, which is the term, or the microcontroller is kind of a small scale computer system. Microcontroller is a small scale computer system. So usually we are using 8, 10, 12, or 16-bit analog to digital converter. So for all of these microcontrollers, we used to have this kind of analog to digital converter: 8-bit, 10-bit, 12-bit, 16-bit analog to digital converter. Why? Because we are going to send to the input, for example, analog signal, and inside is going to be changed digitally to the number of bits required to go to the controller required, to the microcontroller we are talking about. Example on the analog to digital converter is the microphone, strain gauge. This is a sensor. Of course, when I talk about microphone, because sometimes we need to filter the signal coming from the mic, then we are going to amplify it, maybe to save it, to do many processing in it, we need analog to digital converter. So for example, in my computer right now, I am using mic. I am using mic, and the signal my sound is analog, is going to go inside the computer. So if it goes inside the computer, it has to go through analog to digital converter. It has to go through analog to digital converter. So the microphone, whenever there is a computer system or computerized element, we have to have analog to digital converter. Similarly for the strain gauge, similarly for the thermocouple, which sensor again. Thermocouple is a temperature sensor, and voltmeter, as I explained in the previous slide, or digital multimeter, which is the same idea. Voltmeter, if it's digital, we need analog to digital converter. A digital multimeter, if it's digital, we need analog to digital converter. Keep in your mind that voltmeter is the device which measuring the voltage only. Multimeter is the device which measuring voltage, current, resistance, and many other things. The two steps process of analog to digital converter. There are two main steps in the analog to digital converter. They are quantization, then encoding. Where in the quantization, we are breaking the signal down to finite states. A set of a finite states means if the signal is this much, we are going to break it to a finite state. Means I will take this one, this one, this one. So I'm taking 3 states now. We will see this after a while. And encoding is assigning digital word. Means each state will be assigned certain digital word. Digital word means 3-bit value, or 4-bit value, or 8-bit value, whatever. And this one will be assigned certain value, and this one will be assigned certain value. So maybe I can say here is the process of analog to digital converter. The input analog signal will go to sample and hold to make this one, the quantization. Then it's going to go to the analog to digital converter to do the encoding. I hope you catch this point. So the sampling and hold will do the quantization, where the analog to digital converter is going to do the encoding to the signal. And finally, the output going to be maybe 3-bit, or maybe 4-bit, maybe 5-bit, maybe 6-bit, and so on, digital signal. Quantization. Quantization is the process of converting the continuous signal, which the analog signal, to discrete amplitudes, discrete values. This value is analog, instead of having it having continuous change, or if it's a continuous value, instead of having it as a continuous value, we are going to put out of it discrete value, certain value, other value, other value. That's what we mean by quantization. So again, any continuous signal, before we send it to the analog to digital converter, or in as a first part of the analog to digital converter, we need to apply the quantization to it. Quantization means convert it to discrete values. Convert it to discrete values. Now, how many state I can do? How many value I mean, how to split it? Is it randomly splitting? He's saying no. We are having certain possible set or possible state to the analog signal. How to know the number of possible states? The number of possible states is calculated from here. So it's n, which is the number of possible states, equal to 2 to the power n small, where n small is the number of bits. Let us take this example. If you notice here, we have a 3-bit system. 3-bit system. 1, 1, 1. That means a 3-bit system. In this 3-bit system, if I calculate the number of states, it's going to be n capital equal to 2 to the power 3, which equal to 8. What he mean here? It means here we are having, look, we have here, this is 1, 2, 3, 4. These 4 are repeated here in the other side. That means here, here, and here. So until now 4. The new value, these values are repeated. This value repeated here. This value repeated here. This value repeated here. Now, after that, we are going to come with a new value, which is going to be this value. So with count 4. Now 5 repeated, 6 repeated, 7 repeated, and 8. So there are 8 sets. That's what we mean by a number of possible states. So there are 8 states out of this signal. Again, the number of states to be known from the number of bits. Now, when it comes to the quantization, we need to know each set equal to what value. Just now I said it's discrete quantities. Each discrete quantity equal to what? If the analog signal is 10 volt, or the analog signal is 5 volt, or the analog signal is 2 volt, is the set having the same magnitude? Let us see here. He said here to calculate this quantization, the analog quantization is step size. We call it step size. It's to be calculated as V maximum minus V minimum over 2. That means the range over 2. What do we mean by this? Let us look at this example. He said you have 0 to 10 volt signal. 0 to 10 volt signal. Separate them into a set of discrete sets in 3-bit analog to digital converter. So what I need to do here, I need to know how many sets do I need. So we can calculate it from here, n equal to 8. That means this 10 volt will be splitted to 8 different sets, 8 different values. But what is the magnitude of each value? That's what we are going to calculate just now here. So to calculate the magnitude of each value, or what we call it step size, is to be calculated from this equation. So the V maximum minus V minimum over n. Now we calculate n and we substitute. We find that each value will be 1.25 volt. So if I have 10 volt, we are going to split it to 8 different values. It's 8 different sets, where the step size means each set will be different from the other by 1.25 volt. Let us see it in this table. It's going to be clearer. So we will find here that there are 8 sets. 8 sets. We are assuming 0 volt, or sorry, set number 0, set number 1, 2 until 7. They are 8. What is the value of the first one? It's expected to be 0 to 1.25. He just wants to say here that any value between 0 to 1.25, show it as one value. Show it as a one value, maybe 0. Okay? Now let me just express it to understand what you want to do after a while. So let us say it's 0. 0 to 1.25 is equal to 0. Fine. Followed by the second set, which is going to be 1.25 to 2.5. That means any value between 1.25 to 2.5 is to be expressed as maybe 1.25. So remember here, it depends on the type of quantization. Sometimes we consider this value as a 1.25 or 0. But if you consider this is 0, that means the second set will be 1.25. If you consider this is 2.5, the other one will be 2.5. That's the point. So regardless of this point, it's no problem. I just want to put now ranges. I split the signal to ranges. The ranges are increasing by 1.25. That's how we made it. So now my signal, instead of having it as 10 volt, we split it to in these stages, as you see here, as I'm showing in this table. Now we come to the point of encoding. Remember that the steps are one after the other. They are related to each other. They are related to each other. I mean, you cannot say I understand this one, but I cannot understand this one. You have to take the stages, all of them together in the same time. Okay, now the encoding. The encoding, he's saying it's very simple now. Now each set which having certain analog value will be met by digital value. So 0 digitally means 0.000. So now I know that 0, if we get to the input here 0, we are going to get on the output, this is the 3-bit system, we are going to get 0, 0, 0, 0. What about if we are going to the second set, which second one, remember in the previous slide, it's 1.25 to 2.5, 1.25 to 2.5, which consider as this part. If it happened and 1 comes here, I mean, if I don't mean 1, I mean the value of the voltage 1.25 to 2.5. If the case like this, that means we are in this first set, which known to us, first one means this one means this digital. So whenever we have this input on the output, we are going to get 0, 0, 1. If we will get 2.5 to the following value, which set number 2, on the output you are going to get 0, 1, 0, and so on. That's how we do the encoding. Now we will talk about sampling. And sampling means how many samples am I going to take from the analog signal so that it's going to be represented in a good way. What does it mean here? If I have this analog signal and I want to convert it to digital, we need to check how many samples I am taking per cycle. Let's say this is 1 cycle. So how many samples I'm going to take so that I will keep the shape of the signal. So if you notice here, we are taking here certain sample, or the sample here was such that here I'm taking value, here I'm taking value, here I'm taking value, here I'm taking value. So if you look at the representation of the sine wave, it's having this shape. Now, if I improve it a little bit, let us increase the sampling frequency. Increasing the sampling frequency means increasing the number of discrete values to be used to represent the analog signal. So here I'm going to take this one, this one, this one, this one, this one, and so on. So the signal, the discrete signal, are going to look like this. Is it having similar shape to the analog signal? Actually, it's better than this one. Both of them are having, but with this one we are getting better shape. How about if I take this one? If you look at this one, you are going to take these samples. This 1, 2, 3, 4, 5, 6, 7, 8, and so on. So you will find the analog signal, the discrete value. The discrete value look like this. Discrete value look like this. So if you notice here, if you compare it with the analog, you are going to find that it's very close to the analog. So I can say now this representation or this discrete or these discrete values are representing the sinusoidal wave in better way. The best way to represent this one was represent the analog signal is this way with this frequency. Now, of course, it's not always I'm allowed or it's possible for me to go to this much of a frequency. I can say all of them are fine. All of them are fine, but this is the best. So now I can come out with conclusion. The conclusion is saying if you want to get better representation to the analog signal, you need to take a sample such that the frequency of the sampling more than 2 times of the analog. Again, you are going, this is the analog signal which having some frequency. Let's say this frequency is 50 kilohertz. The frequency is 50 kilohertz for this signal. So when you want to represent it, you are going to make the sampling such that sampling frequency such that it's more than 100 kilohertz. If this is 50, we need to find more than 100 kilohertz. How this sampling can be done, we will see it in the next slide. So here I'm talking about, this is the idea I was talking about. The sampling frequency is supposed to be more than 2 of FA, where the sampling frequency is the frequency which will tell us the number of samples to be taken per cycle for the analog signal, and FA is the maximum frequency in the analog signal, maximum frequency or the frequency of analog signal, if you can catch it this way. So let us see in the next slide, we are going to see how the sampling is to be done. First, let's look at this one, very simple example. Then after that, we will go to the sampling method or sampling technique. This question is saying if the frequency of the signal, the analog signal, 200 Hz, what is the minimum possible frequency to sample it? It's 400 kilohertz. That's it. So it's just two of that one. But if I give you choice, keep this in your mind. I want to sample this signal with a sampling frequency of 100 kilohertz, I mean 500 kilohertz or 1 megahertz. Which one is the best sampling? Which one is the best sampling out of these three? Of course, this one cannot, it's not acceptable. It's not acceptable. It's wrong. The first one here, this one is wrong because it's less than double of this. Now the remaining is 500 and 1 mega. 500 is good, but 5 mega is better. It's going to give me better shape to the analog signal. So keep in your mind, the higher the sampling frequency, the clearer the signal going to be. But of course, there are other limitations like the capability of the analog to digital converter, whether it's capable to go for very high frequency or not, that's other case. So here is the sampling done. Sampling is done by comparing the signal which to be sampled with sampling pulses. This is the analog signal which I want to convert it to digital. Here is the signal which need to be converted to digital. So to convert this one to digital, I need to sample it. Sample it means taking certain discrete values representing it. Now, regardless of the frequency or all of these things, how the sampling is going to be done? Sampling is going to be done by comparing the signal with this sampling pulses, such that we are going to go to this electronic circuit, and the electronic circuit will compare them such that when the discrete value, when the sampling signal equal to the analog signal, when the sampling signal equal to the analog signal, the output will be high. Otherwise, it's going to be low. What do I mean by this? Let me put the signals with each other. Hopefully, you can catch them. So if this is the analog, I will put all the signals together. I will put all the signals together on the same figure. If this is the discrete pulses, the sampling pulses, these are the sampling pulses. So they are going to be compared with this signal, with this circuit. They are going to be compared with this circuit. And finally, we are going to find, finally means the rule of this circuit. The rule of this circuit is going to do the comparison. So by the end of comparison, we are going to find if the sampling pulse equal to the analog, the output will be high. So this part will go to the output. Here, between this interval, between this point here, nothing, because there is no sampling. When there is a sampling, comparison will happen. When there is a sampling, and we are going to get signal equivalent to the analog at that time. Again, here the pulse is coming. Here there is a pulse. Here there is a pulse. So the comparison will happen. So out of comparison, we are going to find the analog value will be produced to the output. So this value will be on the output. Again, the same thing. Here we are having sampling pulse. At the sampling pulse, the analog signal will go to the output, the analog value. So by the end of the day, you are going to find these blue signals on the output, which are the discrete values. That's how the process of sampling going to be, or this is how we do the sampling. As you see here, as I'm showing you here, when we compare this one with this one, it will result on the output to give me this one. Okay, here is the sample and hold circuit, then the ADC. In the sample and hold, we are going to generate the sampling signal, hold it for a while until the quantizing circuit take it. How this is happening? Let us keep in our mind that the electrical signal, once it's generated, it must be used or it will be lost. So let us assume that the sampling is done by this switch. So whenever I close the switch, there is a pulse coming on this stage. When I open the switch, no pulse. Close the switch, there will be pulse, and so on. So if I want to send this one to the encoding, the generated pulse will be used by the quantizing circuit whenever a clock pulse coming in. Remember, the clock pulse is something like activation to the quantizing circuit. So whenever the clock pulse comes to the circuit, then the circuit will start its processing. Again, the clock, this one we call it a clock. When the clock signal comes to the quantizing encoder, it's acting as it's the time to start. So once the clock pulse comes to the quantizer will start doing the process. Fine. Now, what if this pulse here generated by the switch during this interval? Means when the clock pulse is low, it's going to be lost. That's why we put this capacitor to keep the pulse in it until it's taken by the encoder or by the encoding circuit. Again, we are going to keep the pulse in the capacitor until the encoding circuit take it. So if it's generated at this time, it's no problem. It's going to stay in the capacitor until this pulse comes. Then once the pulse comes, the signal going to go to the quantizing signal. That's why we call it sample, and hold. I hope you got the point. So that's why we are calling it, again, let me repeat this point, sample and hold until taken by the quantizing and encoding circuit.